Hi guys, in today's session, we are going to see the selection of feedback controllers. So we have studied the feedback controllers as proportional, PI, PD and PID, and we know all the characteristics of the controllers. So now having the characteristics of the controllers, we have to check how do we choose the controller. We should know how do you choose the controller. For that, we have to fix some criteria. Like suppose if you want to buy a mobile, we fix a criteria that one example, camera should be good, or the standby that should be good. So likewise, we fix a criteria and we buy a device which maps the criteria. Similarly, we have to fix the criteria and we have to choose which controller maps that criteria. So in industry, the common criteria, the basic criteria they use to determine the performance criteria is ISE, which is integral square error. Integral square error. So how do we do this? First you have to take a error. We all know that error equal to set value minus process variable or current value. So the error is in terms of time. So that has to be squared and that has to be taken as an integral. So this is called as ISE. Okay. Then similarly IAE is same thing. E of t that should be taken as absolute value. Then take integral. So this is called as IAE. Then ITAE is same. E of t should be taken as absolute value, then multiply by time, then take integral. So this is called as ITE. So like this, we have to perform. Okay, so we have to calculate the value. So what is the value for this? What is the value? What is the value? Then among this, we should have a range. Like if the IAC is within 0.02 to 0.06 means then we can choose we can choose the controller so that that controller should produce this much error. Okay. Similarly, you can fix IAE error as 0.12 to 0.18. Okay, so you have to use a controller so that after using the controller, the response, the response of the system should produce the error is 0.12 to 0.8. If that system produces error, then we can take that one. So likewise, we have to choose the controller based on the criteria. So how do we do that? For example, we take a process. So this is GP of S. Okay. To this process, we have to install a measurement to measure the value GM of S. Then that is compared with the error detector. So here YSP set point, and then this is YM of S. This is plus and minus. So here comes the error. This error is given to a controller transfer function. Then that is given to final control element actuator. Okay. So here we have to take the error and then take a square of it, or they in MATLAB they used to give u square, and then that should be given to a 1 by a. So now what happened? Error is squared and integral is applied. So this should be given to a display unit. We have a display unit in MATLAB. So once you run this when it keeps on the value changing, finally it settled at 0.006, for example. So from this we pick this error as IAC. So here we have to change the controller or change the controller parameters so that your the range should be satisfied. Similarly, if you want to include IAE, then here you have to take, suppose if it is IAE means take the error, and in MATLAB you have absolute unit, A unit, then that should be given to an integrator. Then here you have to connect the display unit. So this displays IAE. Okay. Then the same thing. So here you have IAE, and then if that should be multiplied by T, and then that is okay. So this is ITAE. So likewise, we can connect it and then we can change the controller, or we can change the controller parameters to achieve the same, to achieve the standard range. So for that, to achieve this, we have to change the uh, we have some procedure that we'll study in the next class, like how to tune the controllers. So right now we can have the trial and error of this, and we can check whether whenever you change the parameters, whether the system responds. For example, let me take ISC. Okay, so the error should be 0.06. So I have chosen that KP value something, for example, 8. Okay, so this transfer function is known, this is known, this is known, this is also known to us, set point also known to us. Then I run this system. So if this is the input, so the system is like this, like this, like this. Okay. So this error is 0.006. Okay. So accordingly, in order to get this, suppose if it is 0.6 means, then tune the value. Tune the value, increase the value to 9, 10, so that the error will be decreased. So likewise, whenever you fix a criteria, then based on the criteria, change the controller parameters in such a way that it will fall, I mean, the error will falls under the range, the given range. So for that, we need a criteria. So that is what I wanted to tell you. Once we fix the criteria, then only we can tune the controller. Okay, so for that, criteria is important. Okay, but this method is, I mean, with the criteria, it's very hard to tune the parameters. Like, it is very tedious because we have to keep on changing the value, and then the controller or the whole block is just dependent on the transfer functions, the process transfer function GP of S, sensor transfer function GM of S, and final control element GF of S. Since the control model is heavily dependent on these things, so we cannot tune this, we cannot use this concept appropriately. It gives some ambiguities whenever there is a change in input. For that, what we do is, instead of going this way, first we learn that what is the speciality in controllers, and then that controller suits which process. First we do these assignment, we'll do these prior work, and then we'll enter into the tuning. Okay, so here, so for that, first we should know the importance or the advantage or the properties of the process control. Sorry, controllers. First controller is proportional controller. So what is the feature or what is the advantage of this? It accelerates. Okay, it is faster, accelerates the response of the control process. So whenever you use proportional controller, it accelerates because PE is just KPEP. So only if you change this, automatically the process will be accelerated. So if you use this controller, it is accelerated, but it produces offset. But if you have a process, if you have 1 by s in the process, for example, 1 by s into s plus 1, if this is the process, then whenever you put limit s tends to 0, so this term will be 0, so the output is 1 only. So in that case, error is 0. So you can use proportional controller if your process should have integrators. If a process should have integrators, then in that case, the offset is 0. Okay. So if you want, I can do it again. So consider the GP of S is here one. So this is your GP of S. Okay. And then GC of S is, let us take some two value. Okay. Then GF, GM, this is equal to 1. And then YSP of S equal to 1 by S. Okay. So with this, what is the transfer function? YSP, sorry, Y of S equal to, you have to put GPGC. So it is 2 by S into S plus 1 divided by 1 plus 2 into S into S plus 1. So when you solve this, it becomes 2 by S square plus 2S plus 2, okay, into 1 by S is the input equal to. So now we have to calculate the output value at steady state, which is equivalent to limit S tends to 0, this transfer function, S into. So S is cancelled. Then if you apply 0, so you'll get 2 by 2 as 1. Okay, error equal to input minus output, which is 0. Okay, whenever you use, see here we have used proportional controller, but still the error is 0. What is the reason? Because this 1 by S is in the term. So you can use proportional controller. The plus is it accelerates the response, and also if your system has integrator, then the output, the offset is 0. Okay, or if your system does not have integrator, then what you do is, better you can choose a system for the liquid level. Okay, so from this, what is the assumption? Proportional controller should be chosen for liquid level in a tank or a gas pressure in a vessel, like a simple vessel, or the system should have integrators in their system. Okay, so this is the conclusion. So likewise, if you know the nature or if you know the characteristics of the proportional controller, we will easily map, choose the controller for a particular process, then we'll go for a parameters. Okay, so next one is integral control, we know that it eliminates offset. Okay, but if you prefer elimination of offset, then you have to accept this maximum deviations. So because of the deviations, because the deviation is like this, so it takes time to settle. Okay, if the deviation is little, it takes little time to settle. So if you have more deviations, then the process is sluggish and then long oscillating process. So if we increase the gain Kc value, it produces faster response, but it is unstable. So these are the characteristics for this. So way we can use this integral controller. I mean, so since it is a faster response, so this system should be applicable for the slow process. Okay. Then next comes the derivative controller, which anticipates the future errors and introduce appropriate action. And then it introduces stabilizing effect, because see, this is integral means it keeps on increasing. Derivative means it has to, for example, if this is the input to an integral, derivative controller, it converts this increase to a stable one, stabilizing. So it is unstable, it goes on increasing. But this is unstable means this, it goes on as the time increases, t also. So it goes on increasing. But if you put different derivative controller, this t becomes one, which is constant. So in order to stabilize, we have to use derivative controller. So next we are going to map this with the process. So first, proportional controller. So proportional controller means simple proportional controller can be used, and then you can have offset only for moderate values. For example, if you're, see, you have taken two different values, kc1 and kc2. In the first case, your error is 0.06. The second case, your error is 0.1. So you can choose the value. So moderate values, choose a moderate value so that that offset can be adjusted, can be considered. Or choose a system in which you have 1 by s in the system. Okay, in that case there is no offset. So what do we suggest is proportional controller is applicable for liquid level controller or gas pressure. Okay, because these are a simple system, these system have the chances for 1 by s, and we can have the moderate value of offset also. So proportional controller can be applicable or can be chosen for gas pressure or liquid level controller. Okay, next, if simple PI is not, suppose you are not okay with proportional controller, then use PI. The next option is PI. Okay, in PI controller, offset will be 0, but this produces more overshoot. Okay, but this is for what? This is for I mean, this PI controller is a faster process. So faster process means if you give this faster process to a fast process, because the controller itself faster, and then see, we can say that, see, PI will seldom be used in liquid level or gas pressure, but very often for flow control. The reason is flow control is a faster process compared to liquid level and gas pressure. Okay, so process is also faster, control is also faster, means then your overshoot will be too much. So in that case, you have to use a fast controller to a medium process. So liquid level and pressure process can be applicable for proportional, but in proportional, if you are not okay with the offset, then you have to go for PI controller, because in that the offset is reduced. Okay, so next comes the PID controller. Okay, so here in the PID controller, it is applicable for temperature process or multi-capacity, because the reason is, so here PID means you all know that this introduces offset that is reduced, and then this overshoot is introduced that is stabilized by this derivative controller. Okay, so it is a sluggish process. So the addition of, so since the response is sluggish, the addition of PI controller makes it more sluggish. So in that cases, we have to use derivative action to stabilize it. Okay, so in this case, you have to use this controller that allows higher gains, because this process is sluggish. Higher gains means you're giving more power to that, because the process is sluggish. Why it is sluggish? Because of this I. To reduce the overshoot, D is used. So the process becomes sluggish. So in order to boost the process, boost the performance of the process, we have to use higher gains, and then that should produce faster response. So who produces higher gains? Compensation controller or a multi-capacity process, and then temperature process. So PID is for temperature process. The reason is, so this is because it produces sluggish process. So in that case, you have to go for more gains. And then temperature is a slower process. And then because of the integral, the response is faster. So PID is applicable for temperature controller or multi-capacity process. Okay. So finally, we can say proportional controller is for liquid level. Okay. Then PI is for liquid level with 1 by S. Okay. And it should not be applicable for flow process. Then PID is for temperature. The reason is it is sluggish, so for that it produces more gain. So since it is a slow process, so it takes more time to do this, so you have more gain in this. And multi capacity process also it gives more gain. Composition also gives more gain. So if any process has more gain and that process is a sluggish process, if you use PID controller, the sluggishness will be taken care of this integral, and then it will stabilize this process. So likewise we can fix the controller for a particular process. Okay. So once we fix the controller for the particular process, then we have to go for the normal criteria. One is keep maximum deviation as small as possible. Maximum deviation is this is the input. So this is the out. So this is y, this is set point. So this deviation, keep this deviation as small as possible. Okay, that's first criteria. Then achieve settling time, short settling time. Suppose if this is the input, so this is the curve. So this is the settling time. It takes time to settle. After that, it will not change. So this settling time will be shorter. Okay, so accordingly, so give the controller, then keep on changing the parameters of the controller so that the settling time will be lesser. Like, you know, how, for example, in one controller value, the response is like this. And in the other controller, the response is like this. And in other controller values, the response is like this. See, in this has the shorter. So we can choose this can be neglected. So you have to tune the parameters in such a way that it will achieve shorter settling times. Then minimize the integral of errors. We have seen ISE and IAE and ITAE. So these are the integral of the errors. Okay, so these are the criteria. Okay, then some more criteria is overshoot. So your overshoot is, so this is the input, the system will move like this. So this is the overshoot. Try to reduce the overshoot. For example, this is the tank. So your level is 100 meter. Okay, because of the overshoot, the water may flow like this and it comes in, the water will be wasted. Okay, so that will affect the process. So reduce the offset. Or the tank can withstand only 1000 degrees Celsius. Due to the overshoot, if the liquid is moving to 1800 means this will damage the parts, everything. So keep this overshoot minimum. Okay, overshoot. Then rise time is, suppose if this is the input, then this is the output, means the time taken by the curve process variable to reach the set point for the first time. So here also is reaching the set point, here also reaching, but for the first time, how much time is taken? That is rise time. So try to minimize this also. Settling time, you know. And then decay ratio. Decay ratio is, for example, okay, so this value is 4. And then the next time, the peak should be 1. So this is called as decay ratio. See, then finally it settles. So here the decay ratio is 1:4. So your 4 is reduced to 1. So always we prefer 1/4 decay ratio. Then frequency of oscillation. This oscillation can be controlled. So these are the general criteria. Still now we are using in the industry. Okay. Then time performance criteria. Already we have discussed your ISE is this one, and IAE, and then absolute error. Okay. Then if you want to suppress large errors, how it produces large errors? Because this is square. If you square the term, it produces more errors. So if you want to strongly suppress large errors, then use ISE. Okay. Then for the suppression of small errors, because square produces more error, then absolute produces less error. If you want to suppress small errors, small error means, then choose IAE. Then if you want to suppress that error for long times, because we have included T in this, so the formula is T into error, Okay, so this is your ITA. Okay. Since you want the errors to be suppressed for a long time, then use this error. And then if you want to suppress small errors, so integration of E of t is missed. Okay. So see here, the error is very small. And then if you want to suppress large errors, so it is E square dt integration. If you want to suppress large errors, then concentrate only on IAC criteria. If you want to suppress small errors, concentrate only on IAE criteria. If you want to suppress errors for a long time, then concentrate on ITAE. So like this,